All right. So to start us off today, the quote of the day today is more of an idea of the day. And it's something that I like to think about making strategic use of the learning curve. And in particular, what I mean by that is I think this is good to think about for, bigger picture things like career goals and that kind of thing, but also smaller picture things like when you're studying for an exam. So lots of applications of this kind of idea. We haven't quite gotten to graphing yet, so this graph might, make a little more sense maybe in a couple of weeks when we get to that. But if we think going along the horizontal axis here, if we have something like effort or learning or knowledge or something like that, and on the vertical axis we have something along the lines of like value or utility or yield, is maybe another way of saying it. A lot of times we have a curve that, if I can get my cursor to look right, there we go. A lot of times we have a curve that looks something like this. Let me redraw that. Having all kinds of tech problems this morning. I'm not really sure why. I'll draw it the other way because my cursor keeps wanting to go crazy when I try to put it there at that intersection. Um, so we have a curve that looks maybe something like this. In other words, if I put in a certain unit of time or effort or learning to accumulate some amount of knowledge, it has a certain amount of value, but the next equal amount of effort on the margin has less value. And the next one, the next equal amount of effort, less marginal value still. So in economics, they call this the law of diminishing marginal return, or the law of diminishing marginal utility. And I think this idea applies to academics as well. So what do I mean by this? I mean, if you practice, 10 problems that are, say, solving linear equations with fractions, you'll have put in, a unit of effort and you'll have gotten a certain amount of yield. Now, if you're studying for your exam, is it better for you to put in the time to do 100 of those problems? Or is it better for you to say, okay, maybe I'll practice a little bit of this other section, or, maybe practice things like maybe test taking strategies, things that might not be so obvious to practice, from the course material. Or is it, better for you to say, hey, maybe I'll get an extra hour of sleep and I'll be more awake and alert when I take the exam. So these are all trade-offs, right? We have a limited amount of time and energy and resources, both cognitive resources and physical resources to use. And how we use them, if we spread our effort over several different ideas, we're going to be able to get more yield overall across those several different ideas than if we were to spend it all on, one idea. So I think as far as a study strategy, kind of spend your time in a few different places. Now, of course, if you recognize that a certain topic is a weakness for you, maybe that means you need to spend a little more time and effort on that topic. So that's, the caveat to this. And I think this idea applies to general, say, career goals too. If there's, say, if you're going into, I don't know, let's say nursing, and you have maybe 10 different competencies that are important for nursing, and you're really, really, really good at one of them, is that going to land you a job? If you're not good at the other 9, probably not. But if you're pretty good at all of them, you're probably going to get the job over the person who put a ton of effort into one thing. And why is this dangerous, kind of putting all of your effort into one thing? Well, maybe 2 reasons for that. One is that the person who was the best VCR repairman in the world probably still doesn't have a job today, right? So if you're too narrow, it can be a little bit harder to pivot. And the other thing is, again, on that pivoting idea, if you're kind of a jack of all trades, if, say, a promotion comes up or a job opportunity comes up or something, and you need to be a little bit better at one of these areas, can you get to here if you're already here? Well, sure, you just need to put in, say, 2 units of effort more to get to where you need to be, say, for that new job opportunity or that whatever new opportunity that you're looking at, a career change or something. If you're already, a bit of the ways down this track on, say, 10 different things, then you can put in a couple units of effort to get, to get your competency up in one area pretty easily. If you're kind of at zero in a lot of those different competencies, getting up to speed on them can be challenging. So, and kind of another thing that's related to this is when we choose to put in effort and gain yield in some area, how might we choose those areas? And caveat here, being a math guy, I have a certain perspective of this, but I kind of look at what I call the time constant. This is kind of a big idea in applied math, is like, how fast does something go away, right? If I like pour a little bit of milk into my coffee, like how fast does it dissolve? If the coffee is really hot and if I pour the milk from up high, there's a lot of energy in the system, it's going to probably mix into the coffee very quickly. If the coffee is cold, if it's about the same temperature as the milk and I pour it in very carefully, it might take a long time to diffuse throughout the coffee. So we have kind of slow time constants where things happen slowly versus fast. And what this relates to is, if I learn a piece of information now, or if I gain some mastery right now, how long is it until that's no longer useful to people, whether it's people that I just want to hang out with, or whether it's my job, or whether it's society as a whole? How long until it's no longer useful? So that's kind of on one axis. And on the other axis is the piece of information foundational or trivial? In other words, if I learn this piece of information, does it help me learn other related pieces of information? Or is it like, if I learn this piece of information, I just know it in isolation, it doesn't really help me with anything else? The next piece of information I want to learn, I don't learn it more quickly or better because of the knowledge of the one that I have. And I tend to like slow foundational concepts. So now, of course, math is a slow foundational concept. If you learn how to solve a linear equation, 50 years from now, solving a linear equation is going to be the same process. That is a very slow time constant. It's also foundational. If I know how to solve a linear equation, maybe I can use that as a building block to solve quadratic equations or to solve something else. I try to stay away from fast trivial information, which tends to be things like, some examples. I'm not saying you should never do this. I'm not saying you shouldn't have fun and do these things or whatever. But I mean, as far as, putting in a lot of time and effort into something. So for instance, like sports, right? That really great play that happened this past Sunday, which, which I didn't watch the game, even though my wife is from Kansas City, Kansas City area. Well, if you know about this really cool play, like it's the water cooler talk for that week, like everybody's talking about it, but 2 weeks from now, nobody really cares, right? It has a fast time constant. The value of that knowledge goes to zero pretty quickly. And it's also kind of trivial in the sense that if I know that this really cool play happened, yesterday or 2 days ago now, can I really build off of that? Now, again, I'm not saying you should never, take anything in the fast trivial square into your mind. Certainly, if you enjoy watching sports, but my point is that if you spend a whole lot of time and effort on that, you're kind of spinning your wheels a little bit. What does that look like in a career? Well, say careers like IT have a lot of this fast trivial information, right? So like you learn where this certain function is on Microsoft Word, and you can coach somebody on how to use it. And then they update Microsoft Word, and now you have to relearn all of these things, right? Or you learn where this function is on Microsoft Word. Does that help you understand where this other function is in Word? Or does it help you understand this other idea in Excel? So IT is very much in this kind of fast trivial corner. Math and physics and some of those similar disciplines are up in this like slow foundational corner. And again, I'm not saying don't go into IT, but I'm just saying that realize that if you do go into IT, you're going to be spending a lot of your time uh, kind of, just keeping up with the material. And then these other two quadrants are kind of, plus minus. So for instance, something that has uh, something of a fast time constant, but maybe foundational, maybe this would be something like programming. So you learn a programming language, you learn how to program in C, and you can build a lot of stuff with that. You can understand programming concepts with that. That's more foundational, but it can have a fast time constant as far as learning all the ins and outs of that language because, if you learn C today, well, it's kind of on the way out, right? Maybe learning Rust, maybe that's on the way up, but maybe you choose to learn Rust instead, and Rust never really completely takes off, right? So it's something to think about when you choose a career, which career you're getting into, which kind of what's the expectation of the knowledge and the mastery going to be. Okay, so hopefully that gives you some ideas that apply to more generally, but also to specifically to this course. So when you study, focus on kind of high yield material. Focus on the material that will get you, say, the most points on an exam, or that will best fill in knowledge gaps. So it's an efficient and effective use of your time. Okay, so we have section 2.5, solving equations with fractions or decimals. And I know that a lot of times as soon as the word fraction comes up, people are already a little bit uneasy. But there's a couple pieces of good news here. And I think we'll see the first piece of good news in this first problem. So we're going to solve this two ways. The first way we're going to solve this equation is kind of just according to the general strategy from last time. We're going to simplify. There's nothing really to simplify here. We're going to isolate the variable term and isolate the constant term, right? Isolate the variable term and then isolate the variable and then simplify. Okay, so I have a variable term, a constant term, and a constant term. These have fractions in them, but that's just what they are. A variable term, constant term doesn't matter if it has fractions or decimals or, pi or something like that in it, or just whole numbers. Still variable term plus constant term equals constant term. I want to isolate. Sorry, my allergies have been acting up recently too. So I want to isolate the variable term. I need to get this constant term to the other side. And I'll do that by subtracting 2/3. I have a constant term with a plus. I subtract that term, and I do that to both sides. On the left side, I have 1/3 x, plus 2/3 minus 2/3 goes away. And on the right side, 5/3 minus 2/3. After each step, I always want to simplify. So 5/3 minus 2/3, well, that's a difference of two fractions, but they have the same denominator. So I can just make that a 5 minus 2 all over 3, or 1/3 x equals 5 minus 2 is 3 over 3, which is just 1. So I have 1/3 x equals 1. So that was my one equation solving step so far, and a whole bunch of simplification working with these fractions. I've now isolated the variable term and simplified everything. Now I want to isolate the variable. I have a coefficient of the variable, 1/3. I need to divide by that coefficient on both sides. Yeah, a little more room here. On the left, 1/3 x divided by 1/3, or just number times x divided by that number, just gives me x, so I've isolated the variable, equals 1 divided by 1/3. And again, we remember that if I have a fraction in the denominator, I invert and multiply. I'm going to write this 1 in the numerator as a 1 over 1 times, and I invert my 1/3 to 3 over 1. And I see that this is all going to come out to just be 3, which I'll write like this. And there's our answer. We can plug back in and double check that this works. That might be a good exercise to do in your notes after class. But you can see we just followed the general strategy. There were fractions involved, but we follow the general strategy, we get the answer. But it was a little bit messy, right? We had to do quite a bit in these simplification steps. Since our goal is to solve linear equations, it might be nice to focus more on the equation solving steps here and here, and maybe save ourselves a little bit of effort with simplification. So this brings up the second approach that we could take here. I know I can essentially do anything that I want to one side of the equation as long as I do it to the other side as well. So I could, subtract 1 off of both sides if I want. I could multiply by 10. Or I can multiply by 3 maybe. What would happen if I multiply both sides by 3? I'm going to be very careful here to multiply the entire left side by 3. Right, normally when I multiply or divide, I've already got the terms separated, so it's a little easier to keep track of what's going on. Here, since I'm doing this multiplication step at the beginning, I'm going to be very careful to take my entire left-hand side, multiply it by 3, and take my entire right-hand side, which is just 5/3, multiply it by 3. On the left side, I want to distribute 3 times 1/3 x. Well, 3 times 1/3 is just 1. This just gives me x. Plus 3 times 2/3 is just going to be 2, right? 3 times 5/3 is just 5. So I did one extra step, this multiply by 3 step. This led me to an equation that I think we can agree is probably a lot easier to solve than this one over here with all of these simplification steps. I now go through and do my equation solving steps. Again, I now have variable term, constant term, but these terms don't have fractions in them. I got rid of all the fractions. On the left, I have x plus 2 minus 2 is 0. 5 minus 2 is 3. That was a lot easier. So oftentimes when I clear fractions, as it's called, when I choose to multiply the original equation on both sides by something at the very first step with the goal of getting rid of all the fractions, a lot of times that makes this bit here a lot simpler to work with, right? Could I do this without clearing fractions? Well, sure. Can I follow that general strategy? Sure, it still works. There's nothing wrong with doing the general strategy. It's just that when there are fractions around, a lot of times just following that general strategy blindly, a lot of times that will lead us to a situation where we, at best, have more work to do. And at worst, when we are doing a lot more steps, there's just a bigger chance that we copy something down wrong, that we, make a sign error, we, miss a negative or something, that we do an arithmetic operation wrong. The more steps that I have to do, each step, and this is for me and for anybody else, each step that you have to do introduces a chance of making an error. The more steps we have to do, the bigger the chance that we're going to make an error somewhere and get the end answer wrong. So here I had to do this multiplication by 3 on both sides, but that yielded a very simple equation to solve. So this is the step that we're going to introduce to our general strategy. I'm going to call this step 0 because we had step 1, 2, 3, 4 last time. If you want to relabel your steps, that's fine, but I kept the labels kind of the same as last time and just added the step 0. So it's 0 because we kind of do this before we even think about actively starting to try to solve the equation. Okay, so I want to clear fractions. How do I actually clear fractions? Well, up here, I suppose it wasn't too hard to figure out how to do it. I had the same denominator everywhere. In a problem like this, I have different denominators. So down here, I can't just choose to multiply by 3. But up here, I see if I have the same denominator everywhere, I can just multiply both sides of the equation by that denominator, being very careful to multiply entire sides by whatever number I'm multiplying by. Multiplying through by that denominator, when I have the same denominator everywhere, if I'm careful with distributing and all of that, that will clear all of the fractions. And then I'll just be left with a linear equation of the type that I've already seen a bunch of times and that I've solved before. So let's jump over to the worksheet here. And I'll let you work on this one for maybe 3 minutes or so. So take about 3 minutes, work through this problem, and you don't have to solve it both ways. Solve it with the clearing fractions way. And then if you do that and you still have some time left, then maybe work through the longer way and just to get a little practice with fractions and to see the difference. Okay, so we'll take about 3 minutes here. Okay, we are right at 3 minutes. There was a question in chat that just popped up. When we multiply by 5, we're just canceling the denominator and we're not multiplying the numerator by 5. Essentially, that is correct. We could think of, so of course the denominators here are all 5, so we're going to multiply both sides by 5. And we could take something like 5 times 2/5. Remember, there are multiple ways to think about this fraction. We could multiply the numerator by 5. Maybe in a different context, that would be a good thing to do. Like for instance, if we were trying to get everything into common denominator and then add or subtract or something, in another problem, that might be a good thing to do. But in this case, that doesn't really serve our purposes because we chose to multiply by 5 with the goal of dividing out that denominator. Now, it is important to note that, say in a problem like this, where we don't have the same denominator everywhere, when we multiply by whatever we multiply by, we're going to multiply by the lowest common denominator. When we do that multiplication, we're going to have some factors that divide out, but also some vestigial factors, some factors that won't divide out in each term, and those will need to get multiplied on the numerator. So the answer is kind of, at a baseline in this problem, that's a true statement that we won't end up multiplying anything onto the numerators because this problem is just kind of a warm-up problem. But the more nuanced answer is that it kind of depends on which problem we're dealing with. But that's a good question, though. So I want to distribute 5 times 1/5 gives me 1 times x. Then I have a minus 5 times 3/5 gives me 3. And that's equal to 5 times 2/5 is 2. Then, of course, I do my next equation solving step, add 3 to both sides to isolate the variable term. That also happens to isolate the variable as well. And I get my answer, x equals 5. And again, I can always plug back in and check. And let's do that on this one. So I'm going to plug back in. I'm not going to do any fancy equation solving stuff. I'm not going to move things from side to side. I'm just going to simplify the expression on the left, simplify the expression on the right. In this case, the expression on the right doesn't need any simplification, but maybe in another problem it might. And then just check that the two are equal. 1/5 times 5. In this case, I don't want to cancel the 5s because I eventually want to subtract these two fractions with the same denominator. So if I did 5 over 5, and if I made that 1, well, then I just have to kind of undo that again to combine it with the 3/5. So in this case, I will choose to multiply this against the numerator. And we do see that we come up with something where the two sides of the equal sign are identical. So we have confirmed that x equals 5 is the solution. Okay, so now let's look at this problem. Let me try to zoom in a little bit here. There we go. Now let's look at this problem. And here I've got a couple of things that are a little different. I suppose one thing that's a little different is I have variable terms and constant terms on both sides. So I have maybe a little bit more work to do. my equation solving steps are going to be just a little bit more complicated here. But also my clearing fractions is going to be a little bit more complicated. I see that I have two fractions that have a 3 in the denominator, but I have one fraction that has a 2 in the denominator. If I chose to just multiply through by 3, that would get rid of the fractions here, but not here. If I chose to multiply through by 2, that would get rid of this fraction, but not these. So I need, in some sense, to kind of multiply through by like 3 and 2. Or really what I'll do is I'll come over here. And if you remember, if I said, just this doesn't directly apply to this problem, but just as an example, if I said add 2/3 plus 1/2, the first thing we would do is we would find the lowest common denominator. I would start by just copying down my denominators, 3 and 2. And then for each of these, I would write out a prime factorization. Now for these, the prime factorization is quite easy because these are just prime numbers. The prime factorization of 2 is 2. The prime factorization of 3 is 3. I'll write that kind of in a separate column over here. And then I come down. In my first column, I have a 2. In my second column, I have a 3. And I'll multiply these together. We'll see in some future problems how we might approach finding a least common denominator or lowest common denominator for kind of more complicated denominators. But for right now, we'll just stick with this fairly straightforward one. But we see in this case, if we multiply by 6, basically the product of 2 and 3, we think this will clear our fractions. So if I multiply through by 6 on both sides, again, I'm going to be very careful to multiply 6 by the entire left-hand side. And by the entire right-hand side. Super easy to multiply 6t and then forget about the distributive property and then just do plus 5/3. So I'm going to take the extra step, write everything down very clearly. So much of the kind of line-to-line bit of mathematics and not making mistakes is just with the bookkeeping. Just being really careful with things. Anytime that there's some ambiguity or that you're not quite sure, just write out an extra line. It's much better to write an extra line, take another 5 seconds, and then get the question right instead of getting it wrong on an exam or on a homework where you're going to spend 5 minutes looking for the mistake. Okay, so I've multiplied 6 by the left side, 6 by the right side. Let me distribute. 6 times 3/2. Since these are a little bit more involved, I'm just going to write out one more line here. Now 6t, I can just make that 6t. Now remember, this 6 is kind of a 6/1. It multiplies against the 3/2 like this. And at this point, I want to look for common factors in each of these fractions that could divide out. I could explicitly write out the 6 as 2 times 3 everywhere, and then divide out common factors in my fractions. But here I'll just choose to kind of do that kind of implicitly. So this 2 in the denominator, I know that there's a factor of 2 in the 6 that it can match up with, and then I'm left with a 3. So 6 is 2 times 3. So when I divide out the 2 from the 6, I'm left with 3. When I divide out this 3 from the 6, I'm left with 2. And again, when I divide out this 3 from this 6, I'm left with 2. So for this first term here, I've gotten rid of the fraction. I have 3 times 3 is 9t. Minus 2 times 2, or minus 4. 6t. That one turned out pretty easy from the beginning. Plus 2 times 5 is 10. So I had to do a decent bit of legwork here at the beginning, this kind of 0th step, to get us set up for solving this equation a little easier, and did actually take a bit of effort. But I've kind of kept all of this fraction, this effort with fractions, these computations with fractions, I've kind of put them all together at the very beginning of the problem. And when I get, more comfortable with, say, finding LCDs or with multiplying fractions, I can combine some of these steps, do these a little bit more quickly and efficiently. Certainly, we took it pretty easy. Here, we wrote things out in a few additional steps. So you might not need to. If you don't need to write out that many steps, that's perfectly fine. But if you feel more comfortable writing out more steps, that's a perfectly good strategy as well. Okay, so now we have a linear equation in standard form. Everything is simplified as much as it can be simplified. I can just follow my steps. I have variable terms and constant terms on both sides. I want to isolate the variable term. I'll choose to put the variable term on the side that keeps the coefficient of the variable positive. That's just my preference. If you did it the other way, that's not a big deal. And in the same step, so I'm getting my variable terms on the left, right? I'm getting rid of this variable term. So I'll put my constant terms on the right. I'll move this 4 over by adding 4 to both sides. On the left, 9t minus 6t is 3t, plus 4 minus 4, that go away. On the right, 6t minus 6t, my t's go away, my variable terms go away. 10 plus 4 is 14. I've now isolated the variable term. The variable term is by itself. I want to isolate the variable by dividing through by the coefficient of the variable. And I get t equals 14/3. And then, of course, something that I always recommend that you do in your notes, we won't do it typically because the goal of the lectures and so on is to introduce new topics and work through new topics. So we really focus on that new topic. But it is a good idea when you go back through your notes, pop this t equals 14/3 in up here and make sure that it checks out. Make sure that you get something on the left side and the right side of the equal sign that are in fact equal. So this was a decent bit of work. Give me a second here. My Zoom panel is, for some reason, decided to pop down and stay down. But so this up here, these steps were a decent bit of work, but you can see that by kind of preparing ourselves, by doing that work at the beginning, that made the equation solving steps a lot more manageable. As opposed to, again, like up here, if we tried to, in a sense, kind of embed that fraction work in the equation solving steps, things just, number one, it's just a little jumbled up. Every equation solving step, we just have so much simplification to do. And number two, sometimes we happen to get a little bit lucky and our equation solving steps even become easier as a result of simplifying the fractions. That maybe didn't quite happen here as nicely as it did in the first problem, But still, I think we can definitely say that the equation solving steps, the kind of more complicated part of the problem, not saying it's necessarily always the more difficult part, but maybe the more complicated part or the newer part, those were a lot easier, a lot more manageable when I didn't have the fractions floating around. So this allows us to isolate the fraction work to kind of the beginning of the problem, just get that all out of the way, and then we can focus on solving the equation. Okay, so take a look at this next one, the one with t's here. And work through this one. Let's take about 3 minutes again, I think should be good for this one. So work through this one. If you finish this one up early, you can get started on the next one if you want. You can start thinking about how would you approach this problem? What's the additional nuance to this next problem? And how might you approach that one? Okay, see you in 3 minutes. Okay, it is just about 3 minutes from when we first looked at this problem. So was anybody able to find the lowest common denominator, the number that we want to multiply by to clear the fractions? Okay. I see one answer. Anybody have a different opinion?
Wouldn't it be 35?
Yeah. So I think 35 might be the right one here because we have 7 and 5, and the prime factorizations, of course, are just 7 and 5. So again, a pretty straightforward prime factorization. So 5 times 7 is 35. Yep. I'll multiply both sides by 35. Again, being super careful to multiply by the entire left side and the entire right side. When I distribute and then simplify, what is my next step going to be? What's my next step that I would write down that doesn't have any fractions? Well, 35 times 1/7, the factor of 7 will divide out and leave a 5. 35 times 2/5, here the fraction of, or the factor of 5 will divide out and leave a factor of 7, which will multiply the 2. So that's 14. Going a little quicker on this one because presumably you have, worked through this, at least gotten most of the way through it. On the right side, we have 35t. That's not too bad. 35 times 1/5, again, the factor of 5 will divide out, leaving the 7. 7 times 1 is 7. And 35t plus 7. Sometimes my t's look like pluses. I try to put the little tail on the t, but okay, so now I have cleared my fractions. I don't see any fractions anywhere. I've gotten my equation into standard form. There's no more simplification that can be done or anything like that on either side, no combining like terms or anything. So I note that I have variable terms and constant terms on both sides. I will isolate the variable term. I'll choose to subtract 5t from both sides. That'll leave me with a positive coefficient. But again, if you had chosen to subtract 35t from both sides, that's a perfectly fine approach as well. My variable term is going to end up on the right side because I got rid of the 5t on the left. So I want my constant terms on the left side, which means I'll subtract 7. If you want to break this into 2 steps, if you want to get the variable terms on one side, simplify, then get the constant terms on the other side, simplify, that's perfectly okay. So again, remember last time when I had you kind of write out your own steps, if you broke that into 2 steps and you're more comfortable with that, that's fine. If you're comfortable doing this in 1 step, that's also fine. So on the left side, 5t minus 5t, they go away. Negative 14 minus 7, that is negative 21. 35t minus 5t is 30t. Plus 7 minus 7, they go away. I've isolated my variable term. Now I want to isolate the variable by dividing through by the coefficient of the variable. Dividing by 30. And I see that I get t on the right equals negative 21 over 30 on the left. And then the one last thing I want to do, maybe two last things I want to do, but one more thing I want to do is I want to say, okay, this fraction, is it in lowest terms? Well, there is a factor of 3 that I can divide out of the top and the bottom. So 21 is 7 times 3, 30 is 10 times 3. I can divide out those 3's. And then I'll put the t on the left side because I think we're just a little more used to seeing things written that way. Say t equals negative 7/10. And then, of course, I would plug back in. I check my work, make sure that this is correct. Okay, so let's look at this next problem. This is a similar setup to the previous one. We have fractions involved, but the fractions don't have the same denominators. So again, we'll come over here into some scratch work, find our lowest common denominator. What are my denominators? 6, 4, and 3. So for the 6, I'm going to break that down to 2 times 3. 4, what's 4's prime factorization? What's 2 times 2, right? We could take a couple different approaches here. We could write this as something like 2 squared. That might be the shorter way to write it. But something that I think I would prefer is to write it as 2 times 2. I kind of have a column, this column here, that is kind of the column for one factor of 2. I have another column, this one here, that's the column for a factor of 3. 4 is 2 times 2. I'm going to make another column for this other factor of 2. So this third column over here is the second factor of 2 column. 2 times 2 is 4. 2 times 3 is 6. 3 is just 3, and I'll put that in the first factor of 3 column. And then I'll just come down these columns. This first column is the first factor of 2 column. I'm just going to write that 2 there from that column. I'll write the 3 here from this column and the 2 here from this column. So my LCD is going to be 2 times 3 times 2, or 4 times 3, or 12. Note that if we had maybe just naively said, oh, I can just multiply 6 times 4 times 3, that would give me what? 24 times 3 is 72. 72 is a really big number to try to work with. 12 was a much more manageable number. So getting the lowest common denominator is going to be really helpful. If I multiplied everything by 72, I'd have a little bit of cancellation with the denominators, but I'd end up with these huge numbers that I'm working with, moving the variable terms and the constant terms around. And I'd also end up with an answer at the end that's probably going to be a fraction that's going to need a lot of simplification. So again, taking this first step seriously, or the 0th step seriously, however you want to say it, and being careful with these fractions, getting rid of the fractions, but doing it in a proper way, using the lowest common denominator. This is all, some work that we're doing at the beginning that's going to have a very high yield later on. So I'm going to multiply both sides by 12. Again, being very careful to multiply the entirety of the left side by 12. And same with the right side. I'm going to distribute, and I'm going to go a little bit faster for this one with some of these distributive properties and things. Again, when you go back through your notes, if there's a step that you're not quite sure about, write a little question mark next to it in the margin or something. And when you go back through your notes, fill in that gap, fill in that extra work, make sure that you understand it later on. So 12 times 5, 6. There's a factor of 6 in the 12, and when we divide that out, we get a 2. 2 times 5 is 10. 12 times 3/4. There's a factor of 4 in the 12. 12 is 4 times 3. When we divide out the 4s, we get 3 times 3 is 9. Twelve times 2x is just 24x. No fractions involved in that calculation. 12 times minus 5/3 is a negative or minus. 12 is 3 times 4. The 3's divide, the 4 is left. 4 times 5 is 20. Right. So when you get used to this, when you get comfortable working with these fractions and clearing fractions, this can be a pretty quick and efficient process. Find the LCD, multiply by it on both sides, and then distribute and simplify. We've gotten rid of our fractions. We have variable and constant terms on both sides of the equation. Let's work on isolating our variable term. I'll choose to subtract 10x off both sides because 24x minus 10x gives me a positive coefficient. I like to try to set myself up with positive coefficients of my variable. Since I'm going to be getting the variable term on the right side, I need to get the constant term off of the right side and onto the left side. I'll do that by adding 20 to both sides. On the left side, 10x minus 10x, they go away, and I get 29. On the right side, 20 minus 20, they go away. 24x minus 10x is 14x. I've successfully isolated my variable term. Now I want to isolate my variable, and I do that by dividing through by the coefficient, which one note may look like 19, but is 14. And I'm going to put the x on the left side, just because we're a little more used to seeing it that way. It wouldn't be wrong to say something equals x, but we're used to seeing x equals something. And then 29 over 14. 29 is a prime number. We could pretty easily check, it's not going to be divisible by 2 or 3, not by 5, not by 7. And that's pretty much all that we need to check, right? So 29/14, that's in lowest terms, or there's nothing to divide out there. So this would be our answer. This is simplified. And then, of course, we always want to plug back in, check our work. But I'll leave that as an exercise. Checking your work in these, if you're, a little bit hesitant about fractions, which, most people are, checking your work in these problems just when you go back through your notes, just as an exercise, is a great way to practice fractions, because you can see you're going to have to do a decent bit of work with fractions to plug back in and check and simplify both sides. So just get to kind of brush off some of those cobwebs just to get a little more practice with fractions. That's a great way to get that practice. Okay, so let's do this problem with a slightly more complicated LCD. Let's have you work through one. So work through this problem, and we'll touch base in, let's say, maybe 4 minutes for this one. This one's a little more complex. And if you finish up this one, you can start thinking about how you might adapt this approach to this next problem. So we'll touch base in about 4 minutes. Okay, it's just about 4 minutes. So I wrote over here the calculation for the LCD, but just to quickly note what I did. So we wrote down each of the denominators, 10, 4, and 5. We wrote each of those down over here. 10 factors into 2 times 5. That's its prime factorization. Can't factor 2 or 5 any further. So I just write 2 times 5. I've established a 2 column, and let's say something like a first factor of 2 column. We might be a little more explicit and say it that way. And I've established a 5's column, or again, maybe a first factor of 5 column. 4 factors into 2 times 2. So one of its 2's goes into the first factor of 2 column. The other 2 goes into a new column that is going to establish the second factor of 2 column. 5, well, that's already a prime number. It just is 5 for its prime factorization. It can slot into the 5's column. And then I just come down my columns. 2 times 5 times 2 is my LCD. As a side note, you might have seen 2 times 5, 2 squared, and 5. You might have seen, your instructor might have taught you to just say, write each prime factor down and raise it to the highest power that you see anywhere. You could do it that way as well. It's a little more abstract because we're dealing with exponents and things, and but if you like that way of doing it, it's exactly the same thing. We're just writing out the factors explicitly here instead of kind of combining them under exponents. But if you're more comfortable with using the exponents and kind of doing the write down every factor that you see, raise each one to the highest exponent that you see anywhere on that factor, it's completely logically equivalent, whichever way you like to do it. If you prefer one over the other, I think the columns is just a little bit more visual, keeps things a little bit more sorted out. But if you prefer the exponents way, that's perfectly fine. Just a note on that. Multiplying both sides by 20. And again, maybe I'd be tempted to kind of skip writing this out when I get comfortable with this and try to distribute my 20 into each term. I would recommend not skipping this step because it's so easy just to forget to distribute into one of these latter terms. So just write it out. Let's say 4. I'll make sure to distribute. So 20 times 3/10 x. I know there's a factor of 10 in the 20. 20 is 10 times 2. The 10s divide out. So 20 is 10 times 2. The 10s are going to divide out. I'm left with 2 times 3 is 6x. 20 distributing into 3/4. Well, I really didn't write that 3/4 very nicely. 20 distributing into 3/4, there's a factor of 4 in the 20. 20 is 4 times 5. The 4s will divide out, leaving a factor of 5. Multiplied by 3 is plus 15. 20 times negative x is negative 20x. That one's not too bad. 20 times 1/5. 20 adds a factor of 5 in it. 5 times 4. The 5s divide out, leaving 4 times 1 is just 4. I've cleared all my fractions. I have variable terms and constant terms on both sides of the equal sign. I want to isolate my variable term. I'll do that by adding 20x to both sides. That will keep my coefficient positive. But again, if you want subtracted x from both sides, no problem. You can do it that way. I subtracted 20x, so I'm going to be getting rid of the variable term on the right-hand side and keeping it on the left-hand side. Since my variable term ends up on the left-hand side, I want to get rid of the constant term on the left-hand side by subtracting 15. The left-hand side, I have 26x plus 0 equals 0x. And then minus 15 plus 4 is a negative 11. I've now isolated my variable term. Now I divide through by the coefficient of my variable, divide through by 26. I see that 11 is a prime number. So there's, and 26 is not a multiple of 11. So there's no, there'll be no common factors between numerator and denominator. I would ideally want to go back and check, plug in, simplify, make sure both sides match. And this would be my solution, negative 11/26. Not the prettiest solution in the world. It's kind of a crazy fraction, but that is what it is. Are there any questions so far? Anything that anybody finds confusing or that you'd like to go back and review? Okay. So moving on to the next one, you might have given a little bit of thought to this already with the one on the kind of worksheet side of things. So in this case, do you think that we should clear fractions first, or do you think that we should multiply and simplify first? Any thoughts? And I don't think there is a right and a wrong answer necessarily. Should I multiply and simplify first and then clear fractions, or should I clear fractions first and then multiply and simplify? So we have one vote for clear fractions first. Does anybody want to give their opinion and then maybe give an argument as to why they chose to go that route?
I just did that first because I found it easier to like just get rid of the fractions. Especially with like the way that you've been showing us how to do it this morning. It allows me to simplify it a lot better.
Yeah, so I would I would agree with that. I would say clear fractions first is a good, general first step. Is there anything specific about this problem or about this problem? This one has a similar setup. Is there anything specific about these problems that might make distributing first kind of a sensible option here? Does anybody notice anything about these problems?
It's already the least common denominator that the fraction is for the problem. Like for 5, it's the lowest, like 1/5 is the lowest, row 5 is the lowest common denominator for 5 and 10. And then 3 is the lowest common denominator for 6 and 9.
Yeah, so I would
was
be
gonna
careful with
say it's
using
'cause they're
the term lowest common denominator, but you're definitely on the right idea.
I was gonna
that-
say it's because they're using the distributive property. So you want to like, especially because 6 and 9, so it's like when you divide, it's a little weird. Especially because personally I've never had to do fractions with the distributive property, but it might be a little bit easier, all things considered, when you look at it, because it's like multiplying 5s and 3s, kind of, because of the fact that it's 6x plus 9 and then the thing's 3. And if I remember correctly, you multiply fractions by doing the first one times the other one, but like flipped over? Or am I wrong? I don't remember how to do.
Yeah,
It's been so long. I haven't done math in like too many years.
Yeah. So I think both of you are touching on the right idea. I think maybe a little bit of the semantics, a little bit of the terminology maybe is what's getting in the way, but you both have the right idea. Specifically that the 3 from the 1/3, for instance, 3 is also a factor of both 6 and 9. Or over here, the 5 from the 1/5 5 is also a factor of both 5 from 5x and 10. Yeah, definitely. The terminology is a lot of times one of the sticking points in math is just knowing exactly what all these things are called. What's the difference between a factor and a term? And a lot of that terminology is a sticking point. So yeah, definitely these are what are called the semantics, the kind of, some people say, oh, you're just arguing semantics, but the word semantics comes from the Greek word semantikos, and that actually means important. So, yes, the terminology, the semantics, the way that we use the terms that we use, the way that we use the language, is important in math. Yeah, it is kind of funny. When people like that's like a brush off thing when you say, oh, you're saying this word, do you really mean this? And like, oh, you're just arguing semantics. But yeah, it comes from the Greek word meaning important. So yeah, definitely. But yeah, so the thing that we might notice here, maybe in this specific case, we might notice that if we distribute first, things will simplify nicely. And this is an important point that I want to note, that the more advanced you get with problems, with solving a certain type of problem, let's say linear equations, with fractions, when you're doing your first 5 of these, should you be looking for these things? Probably not. The pace of lecture is always a little faster than the pace of learning because you haven't had a chance to drill them yet, which is why it's good to kind of review notes and things like that, or come back to lectures. So, would I expect you to find this on your own without prompting and just a set of a bunch of random problems? Well, no. But maybe as you get more advanced, as you get more used to solving linear equations, and specifically linear equations with fractions and working with fractions, you might just pick up on, oh, okay, in this particular problem, we have kind of a common factor here. This 1/5 is going to work nicely with 5x and 10. I'm going to distribute that first. You might choose to go out of order or to do something a little differently than the general method if you recognize something. And that's something that's, a little more of an advanced concept. You can say, okay, our strategy is clear fractions first and then do this, then do this. But in this case, maybe it will work a little more nicely if I multiply and simplify first. And I'll show you what that looks like, and then we'll go with the clear fractions first general strategy. So if I distribute, 1/5 times 5x is just x, minus 1/5 times 10 is 2. 1/3 times 6x is 2x, plus 1/3 times 9 is 3. Let's isolate the variable term. Let's get the variables on the right side. And then I want to get the constants on the left side. Over here, I'm left with 2x minus x is x. They go away. X minus x goes away, minus 5. So in this case, distributing first, unlike, working with the fractions up here, where not clearing the fractions first made a big mess. In this case, not clearing the fractions first actually was kind of beneficial because it worked out nicely. This is a more advanced topic that if we have a general strategy, if we say, okay, I know that if I follow these steps in this order, I'll get the solution. That's wonderful to start with. But as you get more advanced, you might recognize that in some special cases, maybe I can deviate from that path a little bit and make life easier for myself. Sometimes you'll recognize that. Sometimes that opportunity will be there. You won't recognize it. You'll go with the general strategy and you'll still get the solution. So, it's not like things are going to blow up or something if you didn't recognize that. If we clear fractions first, we want to multiply through by the LCD of 5 and 3, which is 15. Those are both prime numbers. So we have like a 3's column, a 5's column, and 3 times 5 is the LCD. 15 times 1/5 is 3. 15 times 1/3 is 5. I've gotten rid of my fractions, now I'll distribute. And we can see these numbers are a little bigger because we didn't leverage that initial cancellation that would have allowed us to simplify things just a little further initially. But again, it's not crucial to do that. It would have made this, maybe these numbers, a little more manageable, but not the end of the world. Whoops, minus 45. And so we have 15x on the right side. We have negative 75 on the left side. And we get x equals 75 over 15, while the multiplications of 15 times 1 is 15, times 2 is 30, 45, 60, 75. That's a negative 5. So we get to the same place. We had to do a little more work over here. If we had multiply through and simplify it first, it would have, in this case, turned out a little bit easier. Again, a little bit more of an advanced topic that you can deviate from the general strategy as long as you're still following those fundamental concepts. Like if you do something to one side of the equation, you have to do it to the other side. You can't deviate from that. You can't just turn the left side into a 2 and the right side into an x and say you're done. But if it, so there are foundational concepts like if you do something to one side, you have to do it to the other side. That's a rule. You cannot deviate from that. But there are also kind of optional strategic concepts like we should always clear fractions first. 95, 98% of the time, that's going to be the most efficient path forward. But that is kind of an optional thing, right? It's not a hard and fast rule that you have to clear fractions first. You can switch it up if you want to, or even if you just wanted to try something different and not clear fractions first and distribute and simplify first. If you wanted to go that route, you could certainly do that. So the two things I want to point out here is, number one, sometimes deviating from the general strategy can be beneficial. And that's a little more of an advanced concept, deciding, do I want to take this path or that path? At the beginning, take the default path, go through the steps as they're written. But as you get more comfortable, maybe sometimes you make a different choice. And then the second thing is that there are some things that are mandatory, that are foundational, that you have to do the same thing to both sides. That's a mathematical certainty. And there are some things that are strategic points, or that are recommendations, like clear fractions first. That's usually going to make your life a little easier, but it's not like mathematically incorrect if you don't clear fractions first, if you do something else first, right? So there are mathematical rules that must be followed, and then there are recommendations or things that typically are better that are a little bit more optional. Okay, so I want to move on to this next one, work through this one, and then we'll work through these two together in the worksheet. So here we have 2x plus 3 all divided by 8 plus 3/4 equals 5x plus 1 all divided by 2. Now we might look at this, and let me zoom in on this a little bit, because just with the fractions being written this way, it makes the font a little bit smaller. We might look at this and just say, like, what the heck do I do with this? I'm used to seeing something like 2/8 x, or I'm used to seeing something like, plus 1/2. But if I have this big complicated thing in the numerator, what am I supposed to do with this? Can anybody recommend to me a way that I can rewrite this equation or these terms to look a little more like these terms, which I think might be a little more clear what's going on? If I wanted to rewrite 2x plus 3 all over 8 in a format that's more along these lines, what would that look like? If I want a number times parentheses of stuff, what might that look like? What does this really mean? 2x plus 3 all divided by 8. Well, really what this means is just 1/8 times parentheses 2x plus 3. So this is really just that the same structure, a number distributed through a binomial, distributed through the sum of two terms, just written in a different form. This plus 3/4, well, that's kind of just a standard fraction, and that we can leave that alone. And then I might do the same thing over here. I might write this as 1/2 times parentheses 5x plus 1. You don't have to do this if you're comfortable working with fractions, but again, most folks, fractions are kind of a sticking point. There's just a lot of this syntax, a lot of these details about how we write things like this, that these two ideas can be written in ways that look very different to the eye. So sometimes, getting everything into a format that's maybe a little more explicit, that's a little bit more clear about exactly what's going on, sometimes that can be helpful. But here I want to clear fractions. I'll find my LCD and I see my denominators. If I go along here, my denominators are 8, 4, and 2. 8 is 2 times 2 times 2. That's its prime factorization. So I have a first 2's column, a second 2's column, and a third 2's column. 4 is 2 times 2, so it fills in the first and second columns, and 2 is just 2, so it fills in only the first column. 2 times 2 times 2 is 8. It turns out that our LCD is just 8. I'll multiply everything by 8. I have to use grouping symbols a little creatively here to make sure that I multiply this entire left-hand side by 8. I have to be very careful here. I have two terms. This plus connects this whole bit here, 1/8 times 2x plus 3. That's all one term in terms of what we're talking about here, plus 3/4. This 8 is going to distribute into this bit and into this bit. So let me write this out in another step. Distributing the 8 into the first term here, 1/8 times 2x plus 3. Distributing the 8 into the second term in the square brackets. Now here, I only have one term in here because that 1/2 is multiplying a whole parenthesis. So I can really forget about what's in that parentheses. It's just something in parentheses. I have two things multiplied together. When things are multiplied together, they're part of the same term. So this is just 8 times 1/2 times 5x plus 1. And then remember the associative property that says with multiplication, I can kind of multiply in whatever order I want. I don't need to multiply the 1/8 against this first. I can instead multiply the 8 times the 1/8. 8 times 1/8 gives me 1, leaving me with just 2x plus 3. Plus 8 times 3/4. There's a factor of 4 in the 8. 8 is 2 times 4. The 4's divide out, leaving me with a factor of 2 times the 3 that's already there is 6. 8 times 1/2 is 4. And then times 5x plus 1. Now I need to do a little bit of work. I need to do some simplifying, some distributing. 2x plus 9 equals 20x plus 4, right? There's a lot of steps to this problem, but each step, if we take it one at a time, each step is pretty straightforward, and we're just taking slow and steady steps toward our goal. Okay, now I've got to standard form. I've got all of my terms, like terms combined. I've got variable terms and constant terms on both sides. I need to isolate my variable terms, or my variable term. I'm doing 20x minus 2x, so my variable term is going to be on the right, which means I need to get this constant term off of the right. (20x minus 2x) on the right is 18x, plus 4 minus 4 goes away. On the left, 2x minus 2x goes away. 9 minus 4 is 5. I've successfully isolated my variable term. I need to divide through by the coefficient of the variable, 18. On the right, 18x over 18 is just x. On the left, 5/18. And 18 is not a multiple of 5. 15 and 20 are multiples of 5, but not 18. So this is in lowest terms. And then I would plug back in, double check everything, and that's my answer. X equals 5/18. So let's pop over here, and we'll do these two problems. And I'll kind of work through the problems as time progresses, so you can kind of follow along. We'll take about 4 minutes to go through these two problems. Okay, so start the timer now, and I'll kind of slowly work through them as we are going through this 4 minutes, just to make a little more efficient use of these last few minutes of class. And I just realized my second problem here is the same problem as I had in the lecture. So that doesn't make great independent practice. So as I was looking at it, I apparently copied, I think I did that last time too, that I copied the same problem twice instead of the two different versions. So sorry about that, but you can go back into your notes and, you know, maybe take another look at this one. There are a couple like this in the homework as well that you can take a look at. Okay, so I guess we'll focus just on this first one because I made this flub with this second one. And two approaches here. We could clear fractions. We could multiply through by the lowest common denominator for 7 and 2 is 14. Distribute everything, clear the fractions, then distribute. Be really careful with all of the distributing on both sides. Simplify, isolate the variable term, isolate the variable, get the solution. Perfectly fine approach. Or again, if we had, you know, kind of recognized this nice property here that 1/7 multiplying into 7x minus 14 is going to come out really nicely, and the same with 1/2 multiplying into 8x plus 4, we could save ourselves a little bit of work by choosing to multiply first, simplify all of the fractions, and we end up with actually quite a straightforward linear equation to solve. Either way works. You know, this way is a little more efficient by recognizing this nice property of this particular equation. But again, if you didn't recognize it, no big deal. Multiplying through by the LCD and going from there, perfectly fine approach. All right, and then we spent most of the time on fractions because that's where people have most of the concerns and the struggles. There we go. But we're going to spend, you know, just a couple minutes here on decimals, and we'll probably wrap this up next time. But we know that fractions and decimals, I mean, a decimal is kind of like a fraction. If I want to get rid of the decimals, what can I do? Well, I want to do something like I did with fractions. I see that I have decimals that have one decimal place. If I were to multiply each of these numbers by, say, 10, that would bump each of those decimal points one to the right. And then I'd be able to work with whole numbers or integers instead of decimals. That might make things a little easier for me. So because I only have one decimal place maximum, I'm going to choose to multiply by 10 on both sides. When I distribute, 10 times 1.7 is 17. 10 times 3.2 is 32. 10 times 4.8 is 48. 10 times 9.1 is 91. And since we only have 1 minute, I'll go through this a little bit quickly. These 17x's go away, as do these 91s. 48 minus 17 is 31x. And then we have minus. When we have two negatives, we can add the result and give it a negative at the end. So 123. X equals negative 123 over 31. And 31 times 4 would be 124. And 31 is prime. So this is not going to divide. There's going to be no common factors here. And again, we could plug back in and simplify. It will be a bit of a mess, but we could do that and double check that this is a good solution. So we still get kind of a fraction as a solution, but by clearing those decimals at the beginning, that maybe made it a little easier to proceed through the equation solving steps.